So I mainly come from VTT, but I also have a part-time position at University College Dublin, and I'm presenting here today what we've been doing in EU project Spine, where both VTT and UCD are partners, and then there's also KU Leuven, KTH from Stockholm, and then Energy Reform, which is an Irish consultancy. And we are building an open source platform for modeling. Of course, it's specifically, we are doing it for energy system, but what we're doing is really applicable to any kind of a modeling workflow. This is a 4-year project. We are more than 3 years into the project, and we have a working system. I will present more about the principles of how it works, not really that much about the actual system, but it's there, it's downloadable, and you can try it out. Of course, it's still work in progress, and there are some things we need to improve, but you can work with it as it is. Maybe I should also say it's the whole project is about 30 person-years of effort, and maybe about half of it is for the workflow management. We are also building a new energy systems model in Julia that's taking a lot of the other half, and then we're also running case studies that also take some resource. So that said, let's go forward to the actual presentation. So I'm going to start with the challenges that we've had with modeling. By we, I mean at least in my institute, but I'm also very aware of many of my colleagues in other institutes having similar problems of how do you actually manage the data, from the making sure that the data is valid and you know where it came from. Also, after a couple of years of when someone has actually first gotten some data and put it in some file or wherever it goes, and then that somebody still knows what this was and how it's been made, and has there been any changes, and if there has been, why those changes have been made, and so forth. And as we know in energy system modeling, there is so many different kinds of data that it very fast becomes quite a mess. We've been in that mess, and that's one of the main motivations why we want to do something better here. I think another important point is also that it's used to be, at least in my experience, a little bit an individualistic process, this modeling, where we might have a common model, but everybody is kind of working a bit on their own problem and building their own data sets and so forth. And then when you try to make something work actually together, to make a bit more collaborative effort, it's not so easy to kind of get everything together and get everything actually working. So we are also hoping to facilitate a way of working where it's really actually a collaborative process instead of doing on an individual basis. And this is, of course, something that's been happening in many other fields of science much more strongly than it may have been in the energy systems. And by any means, I'm not saying that everybody has been being individualistic, but I mean, I think there has been a tendency towards that in this field. So we need to be moving forward and getting to a better processes in this field as well. Then the third aspect here is that we need to be able to replicate in order to improve the how believable our results actually are, and also to be more certain that we get rid of errors that there might be, either on the side of the tools. It might be rather difficult to spot small errors in the model code if you don't have anything to compare against. So it would be important to be able to run different models that are trying to do basically the same thing using the same data, to start to notice where the differences come from, and also to be able to correct mistakes from that process. Another source of errors is in data. And of course, there it's also very good that many people work on the same data set instead of everybody kind of working on their own sets of data, even though they are presenting the same, but then everybody does their own mistakes and nobody notices others' mistakes. So hopefully getting there as well with this. Then also, when we try to understand energy systems, there is so many scales involved, both in the temporal dimension. We have power systems that have require models that analyze millisecond scale issues, and then up to decades when we are looking at investment decisions, for instance. And similar in the spatial scale, we need to be sometimes looking at individual processes in high detail in order to really understand how they actually work and how to make them better. And then on other times we are moving to the other edge of the possibilities and looking at the whole global energy resource and so forth. So there is a big modeling challenge there, and there is more. One issue is, how do we actually work? Do we share data or do we share the data processing? I think it's a very nice thing that there's more and more data sharing happening, but I would also like to see more of sharing of the actual data processing, because if you just get data, you might not be so certain how this has been actually processed, this data, and whether it's all valid and so forth. So it can be better to be sharing the data processing tools rather than just sharing the data. And then also this will allow us to be working together in improving the data processing systems we might be using in order to get raw data into the formats and formats what we actually need in the energy systems modeling. We'd also like to have better capabilities to interact with the wider audience, to have easier ways to visualize and also to make it so that those who are really interested in the results can go a bit deeper and be capable of seeing where the assumptions come from and how they might actually influence the results. I even think that it would be quite cool to be able to have such systems that non-expert can also change main assumptions and try to see how those might actually influence the results. So then how to get there, and of course I'm here trying to present those solutions we've been working on. The first one there is about the way we decided to construct this open source package that we've been building. So I'm just first saying a couple of other ways we could have done it in order to have a bit of a reflection here. So I think there is one way to go is to have different pieces of code, Python scripts or whatever, that will do the parts of the process that needs to be done in order to get from raw data all the way to results, and also disseminating the results. And you can do it if you know what you're doing, using different scripts and automating the system using batching and stuff like that, and that's fine. I think that's a fine approach. However, you kind of need to know what you're doing, and I think that while we need people who know what they're doing, we also have quite a big amount of modeling needs, and there should be also opportunities for people who don't want to understand what's going on in the code level, but rather than are just interested in the actual energy systems themselves. So one approach for those kind of people is to use something a bit of
Juha, I think we lost the audio. I'm not hearing you. Am I the only one?
No, the same here.
Same here, no audio from him.
So Juha, maybe your audio is disconnected for a reason I do not understand. Ah, I think it's better now.
You can hear me now.
Yes.
So maybe it was my Bluetooth headset that was losing it. So sorry about that. So there might be these people who want to be modeling energy systems, but don't need to know so much about what's going on underneath. So one way to work is then to use some kind of a monolithic program that can be maybe easy to learn, but then you are really dependent on that particular tool you're using and whatever the developers of that tool will provide for you. So our approach here is to be using this kind of workflow management system where you can make it easy for the regular user so that they don't need to see what's going underneath, but what's underneath is actually all modifiable. It's all based on things like the Python scripts the expert user might be using. So the flexibility is there, but you can rig it up for the modeler type of a user so that they don't need to know everything. And I would even take it further that the systems that we should be actually having in this rather complicated big field with different scales is something where it's not about one person doing things. It should be more about that there is a person that's focusing on part of the whole chain. There is other persons focusing on the other parts of the chain. So this is a picture where I have on the left side there is lots of data processing and importing in order to end up with a database that can then serve different models from the single database. And this is a very central to what we want to achieve in the sense that we feel it's important to get everything into one place or at least one format, because then the different tools can be made to talk with each other in the workflow, because there is a one place where everything comes together using the same language and nomenclature. I will have more about that on a later slide, but just as a note here. So, and probably when a system like this starts to be used, then these pieces here might be something that people do on their own computers, but then the main database that's being shared should probably be a server-based database. And the Spine Toolbox is supporting both a server-based SQL as well as a file-based SQLite databases, so that you can use the mode of working that suits your needs. So I'm taking just this group F here as a bit more example. So it's using the master database, hooking up to that, but it doesn't need to see everything else going on if they're really focusing on this one model in this chain, how to make it better, how to improve the process there. And they might just be taking the data from the master database and then having another database where they add the things that they need for their process. And then depositing their results into the result database that the others might again see. And of course, you can do this in any way you want. This is all very flexible, but this is just an example. And then when one group is focusing on something like this, they can make it into a plugin that the others can pull and start using. The plugin system isn't really there yet. We've been building the putting up the building blocks you need to have a plugin system, but it's not fully implemented at the moment. You can do kind of things like that, but it's not so nice and easy to use as we would like it to be. Then another viewpoint here is that you could do this using a local program. Here's an example of GAMS that people often use for modeling. It works, it's on your computer, you know how it works. You have the ownership of the program. It's in that sense, it's kind of a safe thing. You can also continue working with that as long as the computer works. And then, but it might be so that it's a bit difficult to start sharing these kind of workflows. You might need to do the scripting type of things like the expert user I was showing before. Another approach could be that we could have taken is to start building a cloud application that would be the place where everything sits. And we would be maybe kind of hosting a service for this purpose. And then of course the user would be outsourcing the maintenance of the system, also possibly outsourcing the computation, but it also means that they are outsourcing the ownership of the system. So if something happens, they might not be able to use it anymore. As long as that's a cloud application that they don't own themselves. It of course allows a shared workflow, which is nice. So again, the way we are approaching here is something where you can run on your own machines based on an open source code base. And we are trying to enable computation that can be outsourced. So that you could send your problems to bigger machines or computational clusters or clouds to be computed. Something that's not there yet, but we hope to achieve that during the project. And then also we can share the workflow. So we can take these partial projects, as I was showing, that one model part of the workflow, and then typically using version control as a way to propagate any changes people make and get them to the users in a manner that will maintain the working chain through all of these different programs. And that's something that's not very easy to maintain, because very often if you change something in one part of the in one tool, then it might break something in the other tools. So this is a bit tricky thing, but we are really focusing on how to enable that. And then I mentioned also already the server-based database as an important part of the shared workflow. Then I will move to the data structures, which I think are very central as well to the way this kind of a system should work. So I'm saying here that we should have a generic data structure, and the workflow itself shouldn't care what data goes through. And in order to be able to do this, the data has to include the structure of the data. So it's not just numbers, it's also the structural features of the data. So one example of a structure is that you're just saying that the power plant B is in location X, and that's a relationship, it's structure. You could also say that kind of a model settings can be part of the data, and that might be also important. Basically, this is then a graph. You can present these things as a graph, and we can do that in our data structure, and that picture there is from Spine Toolbox. Furthermore, then when you do this, that your data structure is generic, then the interfaces that display and allow you to manipulate the data can work even though the data underneath changes, even though the structure of the data underneath changes, because it's just using the structural information to be able to show all the data that might be in this generic data structure. It also means that the tools can be made generic when there is a good reason for that. So if you're having a tool that can replace missing values from time series, it finds an empty spot and interpolates something there, you can make that the work with any data that comes through the system. So we are using this kind of a entity attribute value, which is a very common data format when you want to handle data that you don't want to know actually what it's about. You're just trying to facilitate working with that data. There's some enhancements there. We have classes, we have relationships, we have entity types that make it more versatile. Just explaining it very shortly. So there is these entities, attributes, and values, EAV. An example of an entity is an actual coal plant somewhere. An example of an attribute or a parameter is the availability of that power plant, and then you have the actual value for that parameter, 95% here. The value in the system we built, it can be a constant, it can be time series, it can be a time pattern, and we hope that we can also support kind of expressions where you're actually having a mathematical function for the value. That's not there at the moment, but the time series and time patterns and arrays of arrays are possible to insert in the value field. And furthermore, the value can have alternatives. So your coal plant could have an alternative value for the availability and that alternative could then be used in another scenario. I will have a slide about those a bit later. And in order to get more structure here, you can have, or actually you must have a class where the entities belong to. So the coal plant would probably belong to a class something like units. And these entities can be of different types. They can be objects, like this example here, or they could be relationships when they define, let's say, where this coal plant is. It could be a coal plant and Montreal, two different objects, and then their relationship would define this location. And those relationships can also have parameters and values as well. You can form groups out of the entities, and this makes it easier for you to manage whenever you want to make some kind of a common constraints. When you want to say, for instance, that the Canadian CO2 emissions has to be below a certain limit, then you can group all the locations in Canada together and then assign that constraint to that group instead of summing the individual entities separately. And we build it in a way that you can, if you know programming, you can start adding new types here. So these are just the types we currently have. So it's a workflow, so we need to be able to pass data between tools. And we have this generic data structure on one hand, and then we also have this application programming interface in Python and in Julia, where you can access the data. And also in the interface itself, we are giving you a bit nicer ways how you can take data from one tool and send it to the next tool, and it kind of creates a standard way how to do that. And once you start to comply your tool, you make a tool that starts to comply with that standard, then you can very easily start to pass data between different tools that also comply with that standard. We are not just saying that this is the way you must do it. We are also allowing you to do it the way you've been doing it before, typically through files. So we have a generic data importer that currently does these types, and more can be added. And then we are working on a exporter that would do the same thing from our data format to these common formats where different tools might be using. And of course, the exporter and the importer need to be able to understand. The importer needs to be understand what kind of table formatting people might have, and you need to be map those in order to import. And then on the exporter side, you must be able to say in which kind of a order different sets and dimensions should be laid out into the output file that your tool model will need. So we have these alternatives, and you can use these to make scenarios, and then we are working on making it even a bit more advanced by having something we call recipes. So here is an example of the a parameter coal price that has two alternative values, and then we have three different sets of plants that can be also seen as well, they are not quite alternatives here, but you have a base set of plants, and then you have additional PV plants, you have additional wind plants, and you can combine these different sets in a ways that gives you 6 different scenarios. So alternative values, or even groups of alternative values, where you might not just have a coal price, but you could also have a coal and gas price that are part of the same group, and then you can send kind of package them together and make a scenario out of those. And the same on the entity side. So basically, this system will allow us to do set operations on the alternatives to generate scenarios in a really nice way. And this is also something that where we currently have alternatives and scenarios, but we don't have recipes at the moment. Here is then another discussion where it's quite tricky when you are trying to build a single database that could serve very many different models, because of course these different models will have different data requirements. An investment model probably wants less detail, but needs investment data as well. And then another example here is some kind of a N-1 tool that would require high grid detail, but probably no time series, just snapshots of difficult moments in the system. And then how do you actually make it so that you can define what models get what data? So we've been working on this kind of a system where you have in the database side, we are supporting that you can define that this tool will have these features or needs these features, and those features can be provided by different methods. So if your feature is converting energy, you could have a methods where you convert it with a direct relation, a ratio of 40% efficiency or something like that. Or you could have a method that actually gives you part load efficiencies and more elaborate way of defining the operation, the conversion process. And then you can use these methods also as a way to control your they can become scenario data as well. So you can have them as part of the choosing how you want to be modeling. And it makes it very explicit that how do I actually model when you follow this. This doesn't mean that you have to use this, but this is an additional system that we are allowing. You can of course use your own kind of typically models have their own sets of parameters that control how the model behaves, or certain features of the model behave, and you can still keep using those if you want, but we are trying to kind of make it more rigorous if you want to do so. We have something working there, but it's still a bit early phase for that. Next problem challenge is about how do you name things, and it's not just how do you want to call your different things, your parameters and so forth, but also if you are really serving multiple models, they have different names for same things very often. And of course, if you really try to aim in the workflow where you have a single database, or at least something that's more shared, then you need to be having a common way of calling things, and it's not just calling things, it can also be that there are differences in the form of the data or in the structure of the data, and we need to be able to work through this when we are taking data from the shared database to our model specific needs. And the way the Spine Toolbox has been built is that you don't need to use, we are not forcing anything. It's up to you to choose your nomenclature, or if you want to use something that that is shared. I think there are a couple of attempts, at least currently ongoing in the energy community, to build a bit more shared nomenclatures, and that would be great. And you can use those in Spine Toolbox. And then of course, even though you have this kind of a system, I'm not saying it's going to be easy, because all of that, whenever something changes in one part, you need to be ensuring that the chain will still work, and make sure that those transformations are maintained from common shared nomenclature to the tool specific nomenclatures, and possibly back. But I would still say that this common nomenclature is very important, that it will make a life a lot easier, because the alternative is that all the different tools are just trying to discuss with different languages, and you need a lot more transformers in order to maintain that. We have some tools items that can do this common transformations. We need to be adding more functionality there, and if even that what we will manage during the project is not enough, then you can always Python, which is there underneath, and then you can do pretty much anything, which gets to my next slide. No, I've been changing the order. So so when you import data, one should be quite careful, because it's very easy to overwrite what you've done in this kind of a system that I've been showing. So at the current, how we do it is that when you import data to Spine Toolbox using our importer, generic importer, then I think the Bluetooth thinks that I'm not doing anything if I don't do something. It brings all the data into a new alternative, which means that it doesn't overwrite anything. It just brings the data to the database, and then you can yourself decide how do you actually merge that new data with the existing data you might have there. And I think we need to be working more on that. It's an interesting problem, and I think what we have now works fine, but there could be more user-friendly ways of doing things. When you really know what you're doing, you could be overriding as well. Then I'm going to show a little bit of the actual data stuff, what we have there. So showing an example from the bit more complicated data of the time series or array data that we might have here. So there is a view from Toolbox, where you have two nodes that have an electricity demand time series, and the value just says that here's a map here, and the map refers to an array, or actually something that could be a more complex than just a single array. It can be an array of arrays or more complicated structures as well. It's basically a JSON field underneath. So I can take this. This is a list of parameters, but I can also have a view on the data where it's a pivot table. So I've taken if there would be more parameters, they would be here on x-axis, and if there would be more nodes, they would be here in the y-axis, and you could have a pivot table where you can order stuff around. But I can also take this and then expand this map into an index, and underneath there happens to be 7 time steps with the values for each time step, and then I can plot them as well. Our plotting capability is not very advanced at the moment, but we're hoping to provide an easy to use views on your data. We are not aiming to do fancy plotting. We leave that to other tools that Python has, but we want to be able to serve basic needs you could have in the modeling workflow. So I mentioned it's a JSON data. I think we also need to be able to support binary formats when you really have lots of long time series or stuff like that. That should be something to work on in near future. Next one is metadata. We do metadata and allow importing of metadata. I would still say it's a work in progress because metadata is rather complicated. I think I'm running a bit low on time, so I'm not going to go through all of this. So it's just a complicated thing, and to how to make it in a really nice way is not easy, and we are working on it. It's maybe the best way to put it. Right now we have a system where you make changes directly in the database. So this is not about importing data, but this is when you just see that I want to change that number, then it kind of tries to force the user to make a note that I did something. And before it actually stores the data in the real database side, it will ask you to make a message what you've done. We'd really like to get something where you can also have a full history of data if you really want to do that. But you should be able to have control when what data you keep and what data you don't keep. Probably time series data that you can regain using the processing tools you don't want to keep, but if you have you are modifying power plants and power plant data and stuff like that, then it might be a very nice thing to be able to see the history of the data and the metadata of that history. Just highlighting that since Spine Toolbox is a Python program and we have an API to Python, the database, there is an API to the database from Python and from Julia. So you can access the contents of the databases in a nice way through the API, both from Python and Julia, and you can do your scripts that can read those data directly. And then that's of course very nice because there is so much stuff available in Python that you could find useful in the modeling process. And then Julia is nice because it really is aiming to be a fast for mathematical computations. It's still a bit early. It's a rather new language, so I'm not so sure how well it actually compares. Sometimes very fast, sometimes I'm not so sure what's going on. And then we are right now just putting together these Jupyter Notebooks as items in the workflow. So if you know Jupyter Notebooks, they are something where you can kind of write the process of what you're doing, you can document it, and then it would be quite nice to be able to also run those documented scripts in the workflow, part of the workflow we have. And Jupyter can run both Python and Julia. And then we take, when you actually have something bigger to compute, the Spine Toolbox doesn't itself execute the workflow. It just sends it to Spine Engine to be executed. And actually Spine Engine is using Daxter, which is a other open source project that we use to run the execution. And it already does parallelization. So if you have multiple scenarios defined, you can use Spine Toolbox to parallelize those scenarios. Something we will be working on is to how to get that and then to the cloud and to the computing clusters. And one of the reasons why we have Spine Engine as a separate program is that we can just send that to those computing resources outside and not the whole interface, so that we can run the whole system, so-called headless execution, when there is nothing fancy. It's just the actual code that's needed to run stuff. So you would be defining scenarios in the master database, and then these places are where you can actually choose which scenarios you want to run. And since there's 2 tracks here, you end up with 2 times 2. I mean, how many scenarios you have here, and you can parallelize it up to the amount there. You have these different options. Then just trying to say where we are. We are in early deployment mode. We are using at VTT. We have started migrating data and our tools to be running on Toolbox. KU Leuven, another project partner, is using it in national projects. So they're building Julia models for specific purposes and using Spine Toolbox as an interface for that process. In KTH, they are using it for master and PhD student projects, and then our previous or kind of a current energy systems model, it's also relatively recent, has something like 20-30 users in 5 countries, and those we are now trying to help that group to go from kind of an Excel thing towards Spine Toolbox as a front end to the modeling process. And part of that is that we have a couple of Baltic projects where those Baltic projects partners are starting to use Spine Toolbox as the modeling front end for backbone, and the scenarios will be running there. And then maybe the biggest thing right now in terms of where it's going to be used in near future is that there's another EU project, TradeRes, where we will be using Spine Toolbox to orchestrate 2 optimization models and a couple of agent-based models to study market design for future systems. And we try to do this, as I was just explaining, having a single database that can serve multiple models. And there we are testing how this could work and trying to get to data migration as soon as possible. The Spine project itself has 9 more months, and we are focusing on documentation. We have quite a bit of nice documentation. There's more to be done there, and then we have, as you noticed, we have still features we want to have there, and I think we have pretty nice resources still in person months left to do that work. It's going to be a bit hurry, but I'm really hopeful we can do a good job. Then of course we are looking for new funding, EU calls or other sources, and then I would be really happy to have more partners also from elsewhere. I'm listening very carefully what you're thinking there in Canada, for instance. This is an open source project, and I would really like to see it get off the ground, and we don't need to be the only ones building it. I had also some case studies, but I think I'm gonna just leave them be because we are already so much in time. So I think it's time for questions. And
Yes, thank you, Juha. Is there anyone that would like to start with a first question? Nothing has been posted in the chat box, so if anyone has a question, please raise your hand. If not, I will start with one question myself. Maybe it's if I don't see any hands. You said
there is a chat question if you.
Oh yeah, that's true.
So there's a question about how to whether there are any tools to analyze the results well, after they've been executed. And so what we hope to do in Spine project is to, and it's not there yet, but to have, I mean, you saw some example of plotting, but that was very, very basic. So we want to improve that, and we want to hook it up so that you can, once your model runs have been finished, it can automatically bring those plots you're interested in and show them to you. So you can set up this kind of a system to be able to quickly see what did you get out of those runs. And then I think there is another layer there where when you're really trying to get something that you can put in publications, or maybe another thing is to be able to put those some result figures into web pages that would be somehow automatic and can read from result databases and so forth. Those are not something that I see us doing necessarily in the Spine project, but on the other hand, I don't think it's going to be very difficult either, because the interfaces of, let's say, something like Matplotlib is rather simple, and we are providing data in formats that should be relatively easy to get there, and then you can start plotting with those tools that are existing already. And sorry, Luis, I did cut you short.
No, that's okay. I didn't see that there was a question in the chat box. Well, my question is a bit higher level than that. I would say early in the presentation you said that you were hoping for a more collaborative approach to modeling. Have you where in your work have you seen that collaboration improved by using with Spine so far, even though it's not fully it's not done yet, but where have you seen the most benefit for collaboration with that tool?
So I think that it would be nice to be able to say a really, really big example, but I don't have very big examples, so I'm just going to say something small. Where now that we are still fixing bugs in the toolbox, and I guess that's something that will never fully go away. But whenever there is a problem, and I've been working on some demo or something where I want to do something, and then I bump into a problem, it's very easy for me to share that workflow project with the person who can actually hunt the bug down and fix it. And that's an easy way to see how this can actually pan out as a working system.
That's good. And in the data sharing process, or in the data gathering process, have you seen any benefits so far?
We are just getting there. We built also a tool in the Spine project that can read the European. There's the ENSO-E, which is the transmission system operator umbrella organization for Europe, and they have websites where they have lots of data, and we build a tool that can go and get that data. And now next step for us is to start using it in one of our case studies. And so that's an example where someone has built a data processing tool that can import the data and put it in the spine format, and then other people can take it and just use it in their case studies.
All right, thank you. Any other questions? We still have some more minutes. Okay, then if there's no more question, I will take back the control.
Oh, there is a question now.
Oh, you're right. Yeah, it's a question about the co-op task with creating a database out of a set of Excel files for Canadian energy models. What do you think using Spine as software to develop such a database?
Well, I'm of course impartial here, but I would say go ahead. I mean, that's exactly what we've been building this for. Of course, there is the question then that if there is a specific data format you need to be building, you have certain tables and that's that someone has set you those limits, then that's not what we are doing. We have this generic format where the data structure is part of the data. So but I mean, if it's something where you want to have all the data together in a database from which you can then start exporting the data for different purposes, then that's what we have. And I would use Spine, yeah, for sure, for this task.
All right, thank you. So if there are no more questions, well, I will thank you very much, Juha. That was quite interesting. There's a lot of things to digest there, I think, but we will have the chance to learn about a bit more about Spine since you're going to be giving a second webinar in 2 days on the January the 14th, where you're going to make a actual demo of how Spine works. So I invite the people those that are interested at using Spine. That last question, please join us again on that date for that second webinar. If you're not registered yet, just visit the website and you'll see there's a link where you can register.